Hello everyone. Yeah, I will start my today's another coding practice. So today's question is this one. So word rather. Okay. Okay, let me read the question first. In this question, I will be yeah. So a transformation sequence from begin word to the word end word using dictionary word list in a sequence of words begin word as one as to sk such that every adjacent pair of word differs by a single letter. Yeah, so I can change only one character in one transformation. And for every string in word list, note that the begin word doesn't need to be in word list. So I will be given the kind of the bank of the words, which is named begin, oh no, which is named word list. So, but yeah, and my goal is to start from the begin word till the end word. So end word is yeah. So yeah, begin word may not be in the word list. Yeah. However, if endWord doesn't exist in the word list, it means that I cannot make the transformation. Okay. Returns the number of words in the shortest transformation sequence from begin word to end word, or zero if no such sequence exists. Okay. So I kind of find the shortest path from begin word to end word, which goes through the words in the word list. Okay. Let's see. Okay, so let me, yeah, clarify my understanding of my question. So I will be given the word bank like this, cat, yeah. And I will be also given the begin word and end word. So let me think of the case when the begin word is AAA and the end word is BBC. So I have to find all the way from AAA to BBC. And the possible way kind of transformation can be AAA to AAB, then AAC, then ABC, and BBC. Yeah. So this works because AAA to AAB, here only one character is changed. AAB to AAC, only character B is changed to C. AAC to ABC, yeah, only one character. Yeah. And yeah, and ABC to BBC. It's the same. And in that case, no, the number of words in the surface transformation sequence from beginning word to end word. So in this case, I will be returning 5. Okay, so that's my understanding of the question. Yeah. So I think one of the possible approach, which is probably the brute force, is I start from AAA and check every word BAA, CAA, DAA, blah, blah, blah. And also ABA, ACA, ADA, and AAB, ABC, ABD, the blah, blah, blah. And if there is, I will keep forward with that. And in that way, I make sure that I don't come back to the same string, and then I will, yeah, try every possible path, and then I will, yeah, return the global minimum ranks of that transformation path. And yeah, I think that's the brute force approach. So in that way, basically I have to check all the paths. So it could be, yeah, uh, oh yeah, like this. I forget how to code this in English, so let me quickly check. So, so yeah, oh, now remember. So the factorial of n. So however, I can probably there is a better approach. So let me think. I think I can use the BFS approach here. So firstly, I will check every combination of, okay. So the basic idea of my approach is think of the word, think of the, yeah, each word translation to as the breadth first search in the graph. So firstly, I will check AAB, AAC is the path. There is a path between this and this, and this and this. So in this way, I will get the edges from each node to node. If there is, then I will start from the first node, I mean, which is the begin word, and do the BFS to find the shortest path towards the end word. I think it is, yeah. And let me think how much time this would take. So for assuming that number was the n, so firstly to build the um yeah graph, it will take n squared because I have to check all the possible combination as well as the start product, including the start product. So yeah, accurately saying this should be n plus 1 squared. However, it is equal to n squared. Yeah. And so, oh, and also I have to think of the ranks of each word, assuming that on average the ranks of the word is L, it should be like this. And after that, I will do the breadth first search, so it will take up to n time because I have to visit up to one time each word. Yeah. Okay, so that's idea. So let me just yeah write the overview of my implementation. So, and space complexity should be up to n squared, I think, because I have to keep track of the every possible path, and also I have to, you know, um, yeah, in the BFS it will take up to O of n because number of nodes are n. So yeah. Oh, but wait, for BFS, I think it can take n squared because even though I visit only one up to n nodes, from each node, I have to check all the paths. Maybe I don't have to visit it, but I have to check each of them. So it will take n squared. Yeah. Yeah. Okay. So first we build graph, I mean adjacency graph. then do BFS. So let me do with the first three. Okay, so let me assume so the begin word is node -1, and for others, node. Okay. Mhm. So it means so yeah, okay. Yeah. Okay, so let me do it in this way. So begin word is always -1. Yeah. For others, yeah. So this is yeah. So this is the word index. Definition of word index. So it is possible that begin word exists in the word list. So, but in that case, it doesn't matter because I don't have to, I mean, I don't have to visit. Yeah, it is possible that the start word can be visited twice in BFS. However, in that case, it wouldn't be the shortest path. Okay. So let me write code. So this graph is in this way. I can build the adjacency graph. So basically, it should be something like node to adjacent indexes. Yeah. So after that, I will do BFS. So I will write the BFS first and then come back to build the adjacency because build adjacency method is kind of just like the I write it just like the template, so it's not hard at all. So probably I can do it. And I mean, if this approach in BFS part doesn't work, I can save this time to yeah, build adjacency method. So, so being said, I will use the queue. Oh, and one thing I have to take care is if keyword is endWord, I will return 0, not 1. Otherwise, I don't have to take care because, yeah, I mean, I have to take this case because in that case, I cannot put it in the deck. So, I'm implementing the breadth first search, quite typical one. So I have to know the endWord index. Maybe this is the most annoying part. Okay, so let me use, instead of using the index, I will just use, let me just use original word in string in the as the adjacency graph. Because, yeah, it will take a bit more space complexity, but it's okay, I guess, because even though I wrote this as n squared times L, L is the length of the word. So typically in English, it should be up to 5 or 6 or 7 or 8. Yeah, on average, at least. So it doesn't matter that much. I delete these two comments, and then I come back to BFS. Yeah. So now, so, okay, and this is it, and then I will return 0 in the end. This means that I couldn't visit the end word. Here, let me confirm again. So begin word. Oh, and I think this part also takes n squared L in BFS because I mean, so here in line 35, checking if the word is in the visit set will takes all of L. Okay. Yep. So I will, yeah. Okay, so now I will write the build adjacency method. So yeah, so let me write it in this way. So in this way, I can build the whole verse. This can be um duplicate, but it's okay. Or let me just make it in this way. Yeah. So if they're adjacent, I will add it to the adjacency graph. Oh, yeah. And before that, let me just check that adjacency graph. I mean, all the words are the same ranks or not. I will take a look at the constraint. So yeah, okay. So every word has the same ranks, so it's okay. Oh, what I mean, it okay means our adjacent pairs implementation would be much so easy. So cool. Okay, so firstly, I will check if there's the same, I will just continue. Then if it's she1 and she2 are not adjacent and not the same, I will return false immediately. And otherwise, I will append if count plus equals 1. Yeah. So in the end, I will return if count equal 1 or not. Yeah. Probably I can optimize this with returning immediately array return false when diff count becomes 2. But yeah, it doesn't change time complexity, so I skip it for now. Okay, so let me run the code. I'm a bit tired today. Sorry. Okay, so seems like there's an error, so let me seriously, yeah, make amends for it. I mean, amend it. So, yeah, for now I will hide the test case, which didn't work, and single the bug by myself. So, for a geodesic part, yeah, I think it works. It's okay. For our adjacent pairs, yeah, I think it's okay. And oh wait, so every adjacent pair of words differs by a single letter, but it doesn't have to be adjacent. It doesn't have to be AAA and AAB. So it A and AAC are also adjacent. That being said, I think they're with display. Yep. Oh, so this time this worked, but this didn't work. So let me think. Hmm. So let me think. Ah, wait a minute. So, yeah, I think it works. So, hmm, yeah. So I will read the case. It begins with heat and it ends with cold. So let me see this example. So cold is so somehow it seems like it's written here, but end word is cold, which isn't be in the word. Wait, yeah. Oh, so I appended cold in the adjacency graph, which shouldn't be included because yes, so that's the problem here. It shouldn't be included. Okay, so I will run my code. So time remain exceeded. Why is it? Maybe n squared solution doesn't work, but the length of the word race is 5 times 10 to the power of 3. I think it doesn't do that much. Maybe there's an infinite root somewhere. Hmm. Oh, by the way, I think this BFS doesn't take. No, 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 no. Mm. So what should I do? Mm. I think this visit is working, so maybe I have to think of more, optimized approach. Oh, it says the word isn't endWord, so it can be one. All the words in wordList is unique. No, wordlist ranks is 5,000, so shouldn't be a problem with this. I think somehow it does work. Let me already written here. Hmm? Begin word is not end word. Yeah, I think this doesn't take the difference because the ranks of the word is only 10 up at maximum. So hmm, let me just print out visited and current so that they working fine. So that I can confirm that they're working fine. Yeah, it's working. So maybe n squared times L is too wrong. Maybe. Hmm. So how can I optimize my solution? So, hmm. Mm. Let me think. So in this case, I use BFS, but it taking too much time. Mm. I see. So I think one optimization I can make is I don't build the adjacency graph in this way. But instead, for example, if this word, it can be things that it can be adjacent to every word which is in this way, which can be represented in this way in the, I mean, in the regular expression are adjacent. So in this way, what can I do? So firstly, with tours, I map all of these to tours. So, hmm, so okay, so one approach I can make is if I find the word tours, I will make it in this way. And the thing is, I will look for every word which forms in this way. Same for each. Yeah, I will keep track of every regex like this. And also, for example, if I get a new word like hovers, this also can be the regex of hovers pair word. So I will keep track of it in this way. And when I get hovers in the BFS, I will convert it to, I will check every, okay, sorry. If I get the word towards in the BFS, I will check every this, yeah, one, and take a look at each of them. Take a look at each word in this array. So in that way, I think I don't have to take n squared pre-computing for building the adjacency graph. I just need O of n times, I mean, n times L, because for each word, I have to put the word into the regex default list dictionary. And then in the BFS, I will take out L, yeah, regex, then, yeah. I will take a look at each word which exists in the any of the rest. So let me implement in that way. So what I need to do is let me code this one as regex list. Regex map. Reverse regex map. I'm thinking. So this is regex to word. But let me just call it regexes. Regex map. Yeah, regex map. Okay. Build regex map. Actually, it will take more than n times l because I have to build each word, I think. So it will take n times l. Because no, no, n times l squared. Yeah. So this is word, so this way I build the regex map. So after that, what I have to do is right here. So we regex is regex map lib. Oh, so so my next one is I have to convert it to current regexes. So let me just So this is the one. And so here, find regexes. This is a current regex, and then I will take a look at current regex as this map, and then I will get the current word. Then, but if current is equal to prep, I will continue. And so if current is invisible, I will continue. Then from here, I will do the same. So I will append the current words to Q. Oh, then if this is a current word, endWord, I will return current words. Yeah, since that it, let me run my code. I'm too tired today, sorry. Line 87 has the problem. Broke after function definition. Oh, this one. Hmm, maybe. Oh, okay, so here. Hmm? Is this a problem? Function. I think this is in line 87, but it's okay. Ah, simple. Okay. And this. No, 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 no. Okay, this. So I will take a look at each word. Wait a minute. So and I will use range. Okay, it worked. Oh, and it takes only 9 milliseconds. Great. Okay, so it now accepted. So let me quickly take a look at the editorial. Yeah, I will read it later. But anyway, so I will quickly wrap up. So this is the word browser problem, and I use basically BFS. And in my first approach, I built the adjacency graph, and then I used it for BFS. However, it was ended up in time limit exceeded. The problem was probably when building the adjacency list, I took a look at each pair of the word and then check if they are adjacent, and then if true, I appended it to the adjacency graph. But it takes too much time because it takes n squared. So the approach I took instead is using the kind of regex. So for each word, right here, yeah, from each word, I can have up to L adjacency, adjacency word regex. So using that as a hash map, I kind of yeah. Okay, so using that, I built the regex to original word map. Then I used it in the BFS. Probably this is a key. So from the previous word, I converted it to regex and then I took a look at the current word, which meets the regex of that. Yep. So, uh, okay. Yeah. So I will finish with this. Yeah. Okay. So thank you so much. Bye.